I'm very excited to show my work for the last 3 years that I've done here in Oxford in collaboration with other members from the FOA lab, and also Dave May, who's currently at Scripps Institution of Oceanography. And I will be showing a number of numerical techniques that we've developed in theory, but I like that it all falls in the big umbrella about understanding processes that make the ocean floor. So it all starts with the theory of plate tectonics, which for the last couple of decades has created this framework for understanding how the Earth works. And it nicely explains how the surface of our planet moves, but it doesn't quite explain the nature of tectonic plates or how they deform. Essentially, the kinematics of plate tectonics is well established, but the dynamics remain a challenge. And something that has been missing out from the theory is that all plate boundaries are associated with magmatism. And at least from the original formulation and in some of the classical models, magma has been treated as a byproduct and generally excluded from the dynamics. But so we are yet to answer, how does plate tectonics really work? And we can look back to the simplest plate boundary, mid-ocean ridges, where more than 70% of global magmatism is generated. And in the classical view, we have that as two tectonic plates separate, shown in the schematic. Hot material in the interior rises, melts, and then cools down to form oceanic lithosphere. In this model, melt is distributed in a triangular partial melt region and is generally extracted immediately at the ridge axis. So like in this model and many other models, magma has been excluded from the dynamics. But this view from the 1990s starts to crumble, especially because of new data. So a number of studies from the last just few years show a different picture. So in this, I picked a picture of an electrical resistivity map from Reichert et al. 2021 from a transect in the Mid-Atlantic Ridge. And I want to direct your attention to areas of low resistivity in red, such as this one and this one. And we see sort of blobs in the mantle and a sharp wavy interface inferred at the lithosphere-asthenosphere boundary. But what we notice immediately is that however we interpret this data, it doesn't really look as the triangular partial melt zone as suggested by the classical view. And a number of other studies, they also indicate that magma is distributed more widely in the mantle and lithosphere. So essentially, we think that magma plays a key role in the dynamics. So the question that, the big question that I'm motivating my work on is, how does magma create and shape the ocean floor? And to answer this question, we need to go further and consider magma transport, not just in the mantle where it's being formed, but also how it's being transported to the surface. And to do that, we need to include the complex rheological transition between the hot ductile mantle and the cold brittle crust. So magma transport transitions from porous flow in the mantle to sort of magma-filled cracks, such as dikes and sills closer to the surface. And we use a two-phase flow theory to do this, and that takes into account the interactions between melt and solid. So we can also model melting and crystallization together with the mechanics of the two phases. And one important parameter in this theory is the porosity, or the volume fraction of liquid phase. That is because we describe many of the properties of the system based on porosity. And from lab experiments, we know that porosity is generally very low, just a few percentages, and that is already enough to create an interconnected network of melt along the grain boundaries. We also expect porosity to increase, especially in dikes closer to the surface, but that is something that we need to work further, and I will get back to that later. Before I go into scientific applications, I do want to spend a bit of time on the methods, especially because we've developed some new tools, and also because this is a computational seminar series. So in geodynamic models, we generally solve for conservation laws, and I'm going to contrast the single-phase flow theory to the two-phase flow theory. And we usually solve for conservation of mass, which is shown here as the divergence of the velocity field to be zero, or for incompressible fluids, momentum equation, the energy equation, and for two-phase flow, we see that the same conservation laws look very much the same, except that we solve for the bulk system or the phase average properties. And we also, in addition, we also solve for a Darcy's law, which describes segregation of melt through the porous matrix. So when we wanted to, Lorraine mentioned the Riftomat project, we wanted to develop a computational framework that allows us to test the theory, various versions of the theory and various aspects in a very flexible way. And I'm going to show how we've managed to do this. So I'm showing conservation of mass and momentum in the so-called Mackenzie 1984 formulation, which is written here. I apologize for the long equations, but the parameters of interest are the liquid pressure, PL, over here, and the solid velocity, VS, over here. Something very interesting is that if we exclude these terms that I've highlighted in blue, we actually obtain the Stokes equations for an incompressible flow. Essentially, these two terms are the extension for the two-phase flow theory. So we can, if we notice these differences, then we can actually generalize these two equations to describe not just the difference between single and two-phase flow, but also differences between different models. Do we want to model mantle convection or lithospheric deformation? So we can write the same equations in a generalized form, shown as here, where we replaced certain terms or coefficients in these letters in red. So again, I left the pressure and the velocity because those are the unknowns in the system. The D1, D2, D3 coefficients essentially represent the differences between single and two-phase flow. For example, we can model mantle convection or magma dynamics just by modifying these terms. The coefficients A and D1 actually contain information about the rheology. We can model magma dynamics in the mantle and prescribe a viscous rheology, or we can again model viscoelasto-viscoplastic rheology in the lithosphere. And here I'm showing a benchmark for the viscoplastic failure. And the last two coefficients, B and C, we can include more complex physics by including body or inertial forces or compressibility. So by changing or prescribing different coefficients for different problems, essentially we can cover more applications. So what came out of this, we created a flexible and robust computational framework intended for geodynamic modeling that we call the FD-PDE framework. The FD stands for finite differences, and it's solved on a staggered grid, and it's intended to solve partial differential equations, particularly conservation equations, intended for solving single and two-phase flow theory with complex rheology. And it is essentially an overlay built on PETC, which makes use of a new object for staggered grids called the M-stag. And the framework is robust, is testable. We've developed many tests to check our PDEs. And importantly, it is flexible and extensible. So we can build very simple models to test numerical methods or to test simple physical phenomena, but also more complex applications. And essentially, we developed it to solve a number of partial differential equations, such as Stokes-Darcy, or for two-phase flow in slightly different variations, an advection diffusion reaction equation, and we can also couple them in many different ways. So the user only has to describe the type of FD-PDE, or the type of equation, the coefficients, boundary conditions, and the constitutive laws. And this is now published open source on GitHub, and you can find the details of how to access it on in the publication from last year. So going back to the scientific question, how does magma create and shape the ocean floor? I'm going to show you 3 applications where we use the FD-PDE framework to actually do science. So I'm showing here a schematic of many processes, many things closer to the mid-ocean ridge axis. So we have formation of faults, some interplate volcanism, and of course, mantle melting beneath the ridge axis. So I want to focus on 3 parts. First, convective flow beneath mid-ocean ridges. In a second part, convective flow at the lithosphere-asthenosphere boundary. And finally, an application for melting and fragmentation closer to the mid-ocean ridge axis. So the first application, convective flow beneath mid-ocean ridges. The motivation, again, is about contrasting the classical view versus observations. So in the classical view, suggests that melt is concentrated in a symmetric and triangular region, and we have a symmetric corner flow. Oppositely, we have observations of asymmetry from different melt segments, mid-ocean ridge segments from across the globe. So this is a cartoon from the MEL seismic team, which was done on the specific rise. And this cartoon is the summary of a number of studies and observations, and they infer that the MEL distribution is asymmetric. But similar observations have been done on the Juan de Fuca Ridge, in the Mid-Atlantic Ridge, and the Southwest Indian Ridge. And there could be a number of explanations for this asymmetry. For example, for the specific rise, there is asymmetric spreading. So for example, the west is spreading at 100 millimeters per year versus almost half the rate on the east. However, there have been 2 studies, Toomey et al. And Condor et al. In 2002, where they try to force the classical model with either asymmetric spreading or forcing from the mantle, and their findings is that you need unrealistic conditions for both the mantle and spreading in order to obtain the same degree of asymmetry as observed. So something else must be going on. And the way we went about is that, well, we know that buoyancy-driven flows can produce symmetry breaking behaviors. And the simplest example is the thermal convection case shown here for illustration purposes. But the question is what kind of sources of buoyancy we should consider in partial molten rocks. And in addition to the traditional ones of composition and temperature, we also have porosity. And that is because when you have melt in the system, melt is less dense than the solid. Therefore, the bulk mixture is denser than the liquid, but less dense than the solid. During melting and crystallization of partial molten rocks, you can introduce also compositional buoyancy. And that's because I'm referring primarily about the iron and magnesium partitioning between melt and residue. So iron is a heavier element than magnesium and tends to preferentially go into the melt phase. And finally, both the solid and the melt can expand thermally due to changes in temperature. So there has been some previous work on the topic. Of course, this idea has been investigated all the way from the 1980s. So this is a study by Rabinovich, where probably these are the first models of local convection beneath mid-ocean ridges, and they solve for a single phase flow with a parameterized effect of 5% retained porosity. So they only tested porous buoyancy. And fast forward, a couple of more models have explored also porous buoyancy. And in particular, I'm showing the study from some results from CAS 2010, where they used two-phase flow models and included porous buoyancy. And we can definitely see some asymmetry in the partial melt zone. However, very few studies considered compositional and thermal buoyancy. And this is the first application that I've worked on to build a model to include all the sources of buoyancy that I've just described. So I built a model containing to describe two phase two components, where I include a simplified melting diagram shown here, where the liquidus and the solidus are a function of temperature, pressure, and composition. And composition in this case is analogous to the magnesium number to describe the partitioning of iron and magnesium in rocks. And since we're talking about buoyancy, we're also talking about density differences. The density equation of state shown here suggests that the phase density is a function of temperature, composition, but the mixture density is also a function of porosity. So this is the porous buoyancy. In these equations, alpha is the coefficient of thermal expansion, fairly well constrained from laboratory experiments, and beta is coefficient of chemical expansion, which is not well constrained in experiments, also because mantle is multimineralic, while we only want to look at the first order effect of iron and magnesium partitioning. So I used P-melts with thermal engine to estimate the value of beta for melting of mantle rocks, and I obtained a sort of average value of 0.521. And I'm highlighting this parameter beta, which is the chemical expansivity, because it's going to be an important control parameter in the models that I'm going to show. And the geodynamic model essentially solves for conservation of mass, momentum, energy composition, a temperature and porosity dependent viscosity, again for two phases, two components, and where I'm considering the buoyancy in the melt matrix system. So here I'm showing some results from two models. On the left will be the corner flow for comparing the case of an active flow model where I'm considering porous and compositional buoyancy. The maps represent log 10 of porosity, including isotherms in the lithosphere and mantle streamlines in gray. So just for reference, these are sort of model results. They are not that interesting. You can also see plates spreading the surface. The idea is that the systems reach a steady state after a couple of million years. In the case of active flow, the stage is reached a bit later on. The main difference, of course, is that there is the melt distribution looks quite different. But since we're talking about buoyancy-driven flow, we also want to look at the vigor of convection. And here I'm showing maps of the vertical component of velocity. And we can clearly see that in cases of active flow for different values of beta, there is a stronger upwelling component, and including a fairly large component of downwelling at the tip of the melting region. So I've performed a scaling analysis, and I just want to show you the summary of it. And we can describe the dynamics of the system just using two-dimensional parameters. And the first one is so-called the vigor of upwelling, which is the ratio of the maximum upwelling rate or the maximum vertical velocity normalized to the passive upwelling rate for the same set of parameters. The second dimensionless number is the porous buoyancy number, which was first derived by Spiegelman in 1993, and I've extended it to include compositional and thermal buoyancy. So, for example, the compositional term is this one over here, which makes it quite a long expression. So if we plot log of the figure of upwelling versus the log 10 of the porous buoyancy number, we have a collapse of the data. So each point represents one simulation at steady state, and the black line and the gray shaded area are fits from the CAS 2010 paper. Also, very important, this line y equals 0, this horizontal line represents the case of passive flow. So it's where the figure of upwelling is 1. It's very interesting to see that both results, both the fit from CAS 2010 and the results of my simulations fall on the same trend, which is very impressive because there are two different models, different components, different choices of numerical methods, but this scaling shows that we capture the physics of the system. And the physics of the systems are quite interesting and not what we expected, actually. So it turns out that for this case where I was comparing the effect of porous buoyancy and compositional buoyancy, is that they have different, actually of opposite effects. Porous buoyancy tends to enhance upwelling, while compositional buoyancy tends to create a stable stratification in the lithosphere, which stabilizes convective flow. But I started the story motivating some observations of asymmetry. So that meant that we should run models of full ridge and where we don't impose a symmetry axis. And I'm going to show results of full ridge models, but also with forcing on the bottom boundary. And this forcing is done by prescribing a thermal gradient of 0.03 Kelvin per kilometer, which is essentially just 12 degrees over 400 kilometers. This is extremely low forcing, and it's motivated by the fact that previously we consider the mantle to be just homogeneous, but probably the mantle contains heterogeneities, both thermal or chemical. So we wanted to understand the sensitivity of the system due to mantle heterogeneity. And I'm also going to define a degree of asymmetry, shown here, psi. And the important thing is that if psi equals 0, then we have a symmetric partial melt region. And if it's different from 0, it's asymmetric. So here I'm showing some maps of porosity for 4 different cases. On the top, it's the passive flow or corner flow case where there is no buoyancy considered, and 3 cases for different values of beta. And we see that with increasing beta, the degree of asymmetry increases. And we can run more experiments for different forcing, and where we plot the asymmetry versus beta, and we can see that the asymmetry increases with the value of beta. So the summary is that buoyancy enhances asymmetry, and it's very interesting. We obtain very similar results with just very small values of chemical heterogeneity in the system. So if there is any heterogeneity in the system and you take into account buoyancy, the system is very sensitive to that. And we can go even further, and this was the sort of surprising part of the study, that if we increase the forcing on the boundary, so this is a bit larger forcing of about 20 degrees over 400 kilometers, is we actually obtain time-dependent flow. So on the top, I'm showing a porosity map with mantle streamlines, and on the bottom, the residual buoyancy. And what happens is that we have a natural asymmetry in the partial melt zone, and not all the melt can be focused at the ridge axis. So because of plate spreading, some of the melt pools are being forced to crystallize, and you create very fertile solids, shown here in the residual buoyancy maps. So this was very exciting because we started obtaining this small-scale convection at the lithosphere-asthenosphere boundary, and we could obtain some irregular isotherms. And we can do an exploration of the parameter space, and we mapped roughly where this transition between steady state, small-scale convection, and unsteady state convection lies. Of course, that's expected to be with higher degrees of forcings, but also with larger values of beta. So this study motivated another idea, and that is convective flow at the lithosphere-asthenosphere boundary. And that is, again, because of some interesting observations that date back all the way from the 70s and 80s. We generally consider the lithosphere to form by conductive cooling, and we use frequently the half-space cooling model to validate our models or to prescribe the temperature profile in our models. However, even early observations suggested that for older oceanic lithosphere, this half-space cooling model doesn't explain. So, for example, this is data of heat flow. So for ages older than 80 million years, the lithosphere is thinner. So it's the so-called flattening of the lithosphere. And of course, the famous paper by Parsons and Sclater, 1977, addressed this issue, and they came with the plate cooling model, where they fit a trend for the older oceanic lithosphere. However, more recent data actually indicate another picture, that you have undulations in the LAB that seem to be uncorrelated with plate age. And I'm showing again this electrical resistivity map from Reichert et al. 2021 because it's so clear. And we see this very sharp interface that is inferred to be the LAB. Something else from this, both seismic and magnetotelluric observations, is that the amplitudes of the seismic velocity anomalies and the electrical resistivity, they actually require either melt or volatiles to explain the amplitudes. So all these studies, they suggest that there might be melt at the LAB, but then there is the question, how do you form melt there? And I should also mention that there's been some previous work on buoyancy-driven flow at the LAB, and one of the most famous is the small-scale convection, which are based on single-phase flow models with pure thermal instabilities, and they were motivated to explain the flattening of the LAB with beneath older oceanic lithosphere. And fast forward, there's been quite some research recently on this topic in 2D and 3D models, such as this one from 2021, and where we can investigate the dynamics of small-scale convection and how the instabilities form. The problem with these models is that they can only explain observations beneath older oceanic lithosphere, but the studies that I've just shown, they indicate that undulations in the LAB form beneath both new and older oceanic lithosphere. So the question of how they form variations in the LAB beneath younger oceanic lithosphere remains unclear. So we've designed a model to test this. First, how do you create melt of the LAB? And second, can you have small-scale convection beneath the younger oceanic lithosphere, which with the previous model that I've just shown, it showed that it was feasible. So we designed a more generalized model, such as this one, where it's a cross-section parallel to the ridge axis, where the lithosphere cools by conductive cooling, and we want to see how the dynamics changes. And I'm going to show here some model results for a lithospheric age of 20 million years. And this initial lithospheric age can be varied, so we can test the dynamics beneath various ages. On the left, I'm showing a case of no melting. So this is essentially the same as previous work of single phase flow, where the density is a function of temperature. And on the right, a case with melting, and the density is a function of porosity composition and temperature. The top map represents temperature perturbations relative to the initial stage. So we will see the cooling front, but also subsequent instabilities. And on the bottom, these are residual density maps. So brown is denser, blue is lighter. The initial conditions are the same for both cases, and you will see that as with cooling, the lithosphere becomes denser and will tend to sink. So we start forming really Taylor instabilities. I'm not sure it was very clear. The movies are quite fast, but in the case on the right, we also form melting. So as the instabilities form, material is unwelling, mantle material, hot material wants to go up, and it starts melting. So we form these melt pockets, which are very exciting. So I've just paused the movie after 11 million years. So these are two snapshots of the models, and where the melt pools are clearly seen over here with they also are hotter, so they release latent heat, which means that they warm up the bottom of the lithosphere, and they also create chemical heterogeneities. And because the viscosities are a function of porosity, the melt also weakens locally the mantle material. So there are a number of things that and differences between a case with no melting and with melting. And very interestingly is that if we plot the 1300 isotherm shown as here between the initial stages and the evolution after 20 million years, we definitely see that there is more basal erosion and delamination in simulations with melting, which might indicate that if you have melt at the LAB, that can create more undulations. So we think that buoyancy-driven flow may explain observations of asymmetry beneath the ridge axis and undulations in the LAB, but there's more work to be done on this topic. So the last part that I want to talk about is more recent work on melting and fragmentation closer to the ridge axis. And the motivation for that is that, well, in previous models, we had mantle melting and convective flows and lots of interesting things, but generally we extract melt in a very simplistic way. And most of our observations actually come from the ocean floor and happens from the top surface. So there are lots of things happening in between, and we know that magma pathways are quite complex. We have dike intrusions, lava flows, and faulting, and they all depend on spreading rates. And it has been a challenge to model this process in a correct way. That is because we have the transition between the hot ductile mantle to the cold brittle crust, and also the transition to the free surface, which is numerically challenging. But this is the effort of our group from the last 3 years. But the question I want to address is, how does magma-fault interaction affect the mid-ocean ridge axial morphology, fault spacing, and the pattern of abyssal hills? There are quite many things, but essentially we want to look at how magma in the interior is transported all the way to the surface. And there seems to be some systematics about mid-ocean ridges. So fast-spreading ridges show symmetric normal faulting and axial highs, and slow-spreading ridges show asymmetric fault pattern and axial highs. And so, for example, this study by Olive and Dublanchet in 2020 shows the schematic of these observations. And most interesting is there is a lot of variability for slow and ultra slow spreading ridges, and in particular, understanding how detachment faulting happens has been an area of active research. And also in here I'm showing some topographic profiles from Ito and Ben 2008 from the Galapagos Spreading Center and from the Southeast Indian Ridge. And these are different profiles where the one on top is for faster spreading rate, and then the spreading rate decreases downwards. So fast spreading, you have axial highs, and slow spreading, you have axial lows. And it's not clear how the interplay between tectonics and magmatism happens to generate these observations. And there have been two sort of n-member models to explain this. And so in this cartoon, on one n-member is the tectonic stretching, which suggests that any fragmentation of the lithosphere is due to the tectonic extension force, and faults happen because because of the brittle deformation of the crust, and any fault progression happens inwards closer to the ridge axis. On the other end member we have a magmatic extension, which suggests that any extension of the ridge axis is accommodated by dike intrusions. So in this case, tectonics drives the dynamics, and in this case, magma or magmatism drives the dynamics. And of course, there are observations that in favor of both models. So a third category of models try to meet these n-members somewhere halfway. And I call them the M-value models, starting with Buck et al. And subsequent studies. So the idea of this model is, which is based primarily numerically, is that we have a dike injection zone which can accommodate both tectonic extension and magmatic intrusion. And the important parameter in these models is that is this M, which is the fraction of plate separation rate that is accommodated by magmatic dike opening. So a number of studies have used this model for the last 20 years, and valuable results have come out of this, but they all depend on the value of M. And M, there are some studies that also estimate the value of M for different ridge systems. But the one question that at the end of the day is, what is M? Essentially, M is a parameterization of complex processes of diking, faulting, sill emplacement. And we only know that M depends on magma supply and the lithospheric thickness, which is essentially the strength of the lithosphere. However, they are coupled, in my opinion. So, for example, if we look at the dynamics of fast and slow spreading ridges, in fast spreading ridges, the faster you spread, the faster you decompress, the more melt you produce. So you produce a larger melting region. And also the lithosphere is thinner and warmer. So these two, the magma supply and the strength, are connected, and the opposite for slow spreading ridges. The slower you spread, the lithosphere has time to cool, and the less melt you produce. So I've identified three factors that probably affect the system. So again, the strength of the lithosphere, magma, and the extension rate. And they are all interconnected. So for example, the extension controls the extent of melting and the cooling of the lithosphere, but equally magma may facilitate extension. This is one of the hypotheses in the community. And we know that represents a weakening factor for the strength of the lithosphere. However, the strength of the lithosphere may also control the different modes of magma transport and may provide some resistance to further extension. So this is, in order to simplify this view and to put it to test, I'm actually going to remove the extension from this equation for now, but it is in the plan to combine all three of them. So for the purpose of this presentation I'm going to test whether changes in the magma supply controls interaction between faults and dikes closer to the surface. So essentially, I want to test in a simple view something like this, whether having a narrow magma supply might affect a different diking and fault pattern or versus having a wider magma supply. As I mentioned earlier, the geometry of the magma supply is probably controlled by the extension rate, but I'm going to put that aside for the moment. So in order to answer this or to test this hypothesis, we've developed a theory for poro-viscoelasto-viscoplastic flow and combined with a free surface. And I'm going to explain it briefly what that means. It is based on previous work, in particular, the work by Keller et al. 2013, which was one of the first studies to test the two-phase flow theory with viscoelastoplastic rheology. But we know that plasticity poses quite many numerical problems. So we adopted the plastic regularization promoted by Duretz and co-workers for the last 5 years. So essentially means to couple the plastic element with a viscous regularization. So what came out of this? It's actually a new study that was accepted in JGI today. And uses a viscoelasto-viscoplastic rheology and has a hyperbolic yield surface, which represents the Drucker-Prager failure criterion for the shear deformation and a Griffiths criterion for the volumetric deformation. And with this, we've managed to extend the two-phase flow theory to be able to have a continuum model for diking shown as here. So here I'm showing a log of the shear viscosity plot, but also, this blue area is a region with non-zero porosity, which under extension, magma is transported as a dike shown here, which is a tensile fracture. So I've used this theory to create a new oceanic lithosphere extension model. So using the same rheology, and here I'm describing the shear and volumetric components and solving for conservation of mass, momentum, coupled with energy and porosity. And here I'm going to mention that it's still a fairly simple model because melting and crystallization is not included. I'm currently working on it, but in the results that I'm going to show, only melt transport is included. And the model is built using, again, the FD-PDE framework. So here I'm showing the model setup for the simulations that I'm going to show, and it's quite a bit, but essentially we have a section of the lithosphere, we have the interface between sticky water and rock. The model is under extension with a given rate. For the moment, I'm keeping it at 1 centimeters per year. And this extension is balanced by inflow from the bottom. And I'm going to test different geometries of a magma supply in the mantle. And of course, the model has an initial thermal structure and quite many parameters that I'm happy to answer questions about. Okay, so looking at some results, I'm going to show 3 simulations where I'm testing the size of the initial magma supply. And for an initial lithospheric age of 2 million years. So this B parameter just controls the lateral extent of the magma region. On the left, I'm showing the particle in cell sort of field or markers to look at the formation. In the middle is the second invariant of the shear strain. And on the right, maps of porosity with the temperature contours. Okay, so I'm going to start playing them, and we have porous flow in the mantle. And with further extension, when the magma reaches the brittle part, which is sort of the isotherm of 1,000 degrees Celsius, we start diking. So these are dikes. And we also notice that, well, if we have a narrow magma supply, we obtain only one dike. But if we have a wider magma supply, we have multiple dikes. And if we take a snapshot at 400 kiloyears, that's essentially the case. So the dike, the width of the diking region reflects the width of the magma source at the brittle ductile transition. So which is represented by approximately by the 100 degrees isotherm. We also notice some weak localization of surface faults by dikes, but very interestingly is that the depth of the dikes and the maximum porosity reached in the dikes seems not to be correlated with the volume of the magma. But this is something that I've tested with a constant magma source, so that can change a bit later. What happens if we have a variable lithospheric age? So for example, I'm showing here a model where the initial conditions have a slope in the isotherm. So the ridge axis is a bit hotter. And this is, again, the model. Essentially, it looks the same, but there is more localization in the shear faulting closer to the ridge axis. And what we notice is that if we have magma ascent beneath a lithosphere of constant age versus variable age, magma ascent is faster, but that's because the formation is more focused in the second case. And here I'm going to show one of the last models, and this is a case where we have a continuous magma source. And of course, this was motivated because I noticed that the maximum porosity in the dikes stays the same and it doesn't reach the surface. So what happens when we have a source of magma and the bottom boundary? So I'm going to show some results. So we have, again, and lots of things happening, but also some interesting pulsing from the magma that is completely new. So if we take each individual stage separately, we have an amagmatic rifting with porous flow in the mantle. We start, after a while, we have the first dike propagation, and then once this dike reaches a saturation level in the lithosphere where it cannot propagate further, multiple dikes happen laterally. And with further magma supply from depth, we have also more ascent and widening of the dike. So magma also travels laterally. And very interesting is that there seems to be a dike system fed by magma pulses towards the end stages of the simulation. So with that, I bring some short conclusions and I'm open for questions. The idea is that I've presented a number of models of processes that make the ocean floor, and the buoyancy-driven flow seems to explain observations of asymmetry beneath the ridge axis and undulations in the LEB. And there is more exciting work coming up. And we've also developed a new poro-viscoelasto-viscoplastic flow in order to understand the interaction between tectonics and magnetism.